A projectile is an object that can be thrown, it could be kicked, it could be shot out of a cannon, it could be anything that basically proceeds with no additional force on its own. Another thing that you're going to see a lot in this particular unit is something just being dropped. So anything where it's continuing without like an engine to keep it going on its own. And the projectile motion formula you can see on your worksheet there, we need to talk about what these different things stand for. So h of t, this is just function notation, and h of t is basically talking about the height of the object or of the projectile at time t. So the height at time t. T is your time, and that time shows up, you can see t shows up multiple times on the other side of the equation. That's your input variable, which is why it's inside the parentheses over here in function notation. A here, this stands for the acceleration of the object. Okay, and this is due to gravity. So gravity pulls an object back down to Earth, and it's going to make its height decrease. And we can use the same number for the acceleration on every single problem, depending on if the problem gives information in feet or in meters. So if the problem uses feet, we're going to plug in negative 32. And notice that we're taking 1/2 times the acceleration. So negative 32 isn't going to be part of your final function there. You're going to take half of that to get negative 16. But that's if the problem uses feet. If the problem uses meters, what you're going to plug in is negative 9.8 meters per second squared. And that's negative because, again, the gravity pulls items to the earth. So gravity decreases your height, right? Gravity decreases height. So we use that negative number because our function is for the height of that projectile. V sub 0, we call that V naught, and this stands for the initial velocity of the object. How quickly is it initially, being kicked or pushed or whatever it is. So we read that as V naught, and if the object is just dropped, then there's no initial velocity. So sometimes this might even be 0. And then h sub 0, or h naught, this stands for the initial height of the object. And this obviously changes based on how that item is initially thrown. If you throw something and you're around 5 feet tall, maybe that height of the object is 5 feet at the very beginning. Or if you kick it off the ground, its initial height might be 0 feet. So this just varies based on whatever that particular scenario is. So let's look at an example. I think more of this will make sense once you have an example to kind of look through. So it says Scott throws a ball with an initial velocity of 14 meters per second. His arm is 5 meters above the ground when the ball is released. That's pretty high up, so he must be standing on a platform or something. So identify the value of each variable. A equals, remember A stands for our initial velocity. And because everything in here is talking about meters, we're going to be using that negative 9.8. And we'll simplify our equation here in a little bit. But we know A is negative 9.8. The initial velocity, they tell us, is 14. So V naught is 14 meters per second. And then, like we said, it's 5 meters above the ground when the ball is released. So your initial height is 5 meters. So if we plug everything back into this formula, we're going to have h of t equals, so we always start with h of t equals, and remember it was 1/2 a squared. So in this case, if we do 1/2, well, our a was negative 9.8, and then, t squared, a times t squared. So then we'd have t squared at the end. So 1/2 of negative 9.8 is negative 4.9, and then we'd have t squared. So that's how we're going to start it, negative 4.9 t squared. And then the rest of the formula says plus v naught t plus h naught. So plus v naught was 14 times t plus h naught, which was 5. So there's our formula. And we're going to do everything else with this formula in Desmos. So let's go ahead, go to Desmos, open that up, and plot that formula. So we can see it in Desmos here, and you might want to change your scale. You might want to zoom in or zoom out, or change it here on your on the custom thing where you can actually adjust things a little bit better. So maybe I want it to just go from -1, and it looks like really all I would need is for it to go up to like 5 seconds, because we know that the x-axis is our time and the y-axis is our height. We already talked about this in the last video. So that basically is just saying that it's going to take less than, look at that, even 3.5 seconds for it to hit the ground. So let's go ahead and kind of sketch this on our notes so that we can take a look at what all of that really means. So we have our x-axis, time, and our y-axis, height. Now this is in meters. Our initial height was 5 meters up. So at here, 5, we have our y-intercept. So we can actually answer this question down here. It says, what does the x-intercept represent and what does the y-intercept represent? We already talked about the y-intercept is your initial height. It's that starting height of the object. So then it goes up like this and it comes down and it hits our x-axis, and that's at our x-intercept, and we know that's the time when the ball hits the ground, right? So time when the ball hits the ground. And we don't have to label too much else. It says sketch the graph below with titles and labels on both axes. We're just going to do a very quick little sketch there. Now for the rest of this, we can figure out everything from Desmos. So calculate how high the ball will be 1 second after it's thrown. So using Desmos, it's not too hard to do this. We want to figure out exactly what my output here is when my input is 1, when my time is 1 second. So if you remember one option, you can take this list, you can turn it into a table, and what we want to do is we want to plug in 1. So if I type in 1 here, is it going to let me? Let's see. If I type in 1, well, it might not let me. You know what we should do? Let's do this. We're going to change all of this to be in terms of y and x. So I'm going to make that y, and I'm going to change my t's to be x's. I wonder if this is going to help us. So if I just use this, let's make our table now. Is that going to help us out? So if we try to make the table, look at that, it helps us. So maybe in the future, instead of using h of t on Desmos, just use y and x. But right here, we can see at 1 second, our output is 14.1 meters. So there's your point right there. That answers the question that we were looking for. Calculate how high the ball will be 1 second after it's thrown. That's going to be 14.1 meters. Now, there's no reason that you couldn't figure that out on your own. You just have to evaluate h of 1, which basically just means plug it in. You're going to do -4.9 times 1 squared plus 14 times 1 plus 5. It's just a lot easier if Desmos can tell you that same answer. The next question, determine the time at which the ball reaches its maximum height, and what is that height? So the time when that happens, this is the x-coordinate of our vertex. But what is the actual height? This is the y-coordinate of the vertex. So the bottom line is here, we need that vertex. So if I am on my graph, if I click out here, anywhere on the graph, it's going to kind of help me to pick out just random points. But if you click close to that vertex at the top, it's going to find it for you. So it looks like we have 1.429, comma 15. So it looks like our time here with the x-axis, let's just go ahead and round it. We can say 1.4 seconds is the time when we hit that maximum height. And then for our actual maximum height, that was 15 meters. And we always want to label our answers just because we're in a contextual problem. We can actually say what these numbers mean. We don't want to just put 15. The last part, determine when the time when the ball hits the ground. So we know again that that's going to be our x-intercept. So again, going back to Desmos, we just need to find the x-intercept down here. Click anywhere and it's going to show up. So we see 3.178. So we'll just round that to the nearest tenth and say that that's about 3.2 seconds. So if we wanted to label this up here, this was going to be 3.2. Okay, so go ahead and take a look at the last one. Example 2, Mr. Jackson is golfing one fine Sunday morning. He stops when he gets to a bridge over a river to enjoy scenery. When he looks down, he sees an alligator. He drops a rock from the bridge to see what the alligator will do. He is 50 feet above the water. So this time we are in feet, and that's important to keep in mind because that's going to change our acceleration. Remember back in our original notes, acceleration due to gravity, if it's in feet, we're talking about negative 32. So we're going to do 1/2 AT squared. So for this one, 1/2 times negative 32 t squared is going to give us our first term. Half of negative 32 is negative 16. So negative 16 t squared is going to be the first part of our equation. Oh, I guess I should have put the negative 32 in here. The initial velocity, because this rock is dropped, there is no initial velocity. So it's actually going to be 0 there. And then the initial height, he is 50 feet above the water, so 50 will be our initial height. So we could say plus 0t, but since there's 0 of them, we don't really have to include them as part of the equation. So I'm just going to write the end part, the plus 50. So we're going to graph this on Desmos. So go ahead and get to Desmos and plug that in. Like I said, maybe I would just use y and x in the actual Desmos program. Okay, so I went ahead and I plugged it in, but I adjusted my screen so I could see the important stuff. Obviously, our time is the x-axis again, y-axis is height. The rock starts up here at 50 feet, but it's dropped, so then its height is decreasing over time. And it looks like it takes between 1.5 and 2 seconds for that ball or that rock to hit the alligator or the pond below. So let's go ahead and sketch this. And the biggest thing is just recognizing that you're not going to have the entire parabola over here. It's going to go down like this from that 50 feet in the air. So this is going to be 50. This is our height in feet. This is our time. Okay, so how high is the rock after half a second, 0.5 seconds? Then just go into Desmos, do the same thing that we did before. Get that table and you can type over any of the x values. If I plug in 0.5, we get out 46. So that tells us that the rock is 46 feet in the air, which makes sense. After half a second, it should be lower than where it started. When will the rock hit the water? So that's basically like asking when it hits the ground. We're looking for that x-intercept there. So again, come out here and just click anywhere close. It's going to give you that point. So it's 1.768 seconds. So 1.768 seconds, let's just round that to 1.8 seconds. Okay, so that means right here, this is about 1.8. And last, when will the rock be exactly 30 feet above the water? So this is a little bit different. So look on Desmos. Here's where 30 feet is, right? So I know this point right here where the output is 30, I'm trying to figure out what that input is that goes along with it. So if you came over to your table, it's not going to let you change the output section, right? So it's not going to allow us to say, let me plug in 30 for y and solve for x. But something else that you could do instead is why not graph the equation y equals 30? It's that horizontal line right there. And then Desmos will give you an intersection point if you get closer to it. So is it going to let me? Let's see. So we can figure out about where that is. Let's see. I'm not sure if it's going to let me do that. I actually think it doesn't want to give me the intersection point right now because we converted it to a table. So let me just type back in that equation one more time. Sometimes Desmos can be funky. So we have it again, and now that the actual equation is graphed versus just the table format, look, it gives me that intersection point. So I can see right there that at 1.118 seconds, that rock is going to be 30 feet in the air. That's the intersection of my parabola and my horizontal line at y equals 30. So about 1.1 seconds, that rock will be 30 feet up in the air. So 1.1 seconds. So if Desmos is ever funky, just try to type the equation in again, and that should work out for you. But go ahead and do the practice, and hopefully you feel pretty comfortable with Desmos for projectile motion.